We open on silence. Not the silence of a quiet room, but the profound silence of space itself. A silence so complete that no human has ever experienced it on Earth, where molecules of air constantly bombard our eardrums at approximately 10 to the 823 collisions per second, creating the baseline hum of existence. In space, there are no molecules to vibrate, no medium to carry sound waves. An explosion occurring just 1,000 meters away would be utterly, absolutely silent. This is where our story begins. In the silent void where the strangest objects in the universe lurk, waiting to be discovered. On April 27, 1967, a young graduate student named Jocelyn Bell was analyzing paper charts from a radio telescope at Cambridge University. The charts showed data from a survey of the sky, looking for quasars, distant, extraordinarily bright objects powered by supermassive black holes. But on this particular day, Bell noticed something odd. A little bit of scruff on the paper, a signal that didn't look like noise but didn't look like any known astronomical object either. It was a regular pulse, repeating every 1.337 seconds with astonishing precision. The regularity was so perfect that Bell and her supervisor, Anthony Hewish, half-jokingly called it LGM-1 for Little Green Men. They seriously considered the possibility that they had detected an artificial signal from an alien civilization. What else could produce such precise, regular pulses? The signal was coming from a fixed point in the sky, from a specific location among the stars. It wasn't interference from Earth, they had checked. It wasn't a satellite or aircraft. It was something out there, in deep space, pulsing with the regularity of a cosmic lighthouse. Within months, Bell discovered 3 more pulsing signals, each coming from different locations in the sky, each with different periods. The Little Green Men hypothesis collapsed under the weight of multiple detections. It seemed unlikely that multiple alien civilizations would all be broadcasting at us simultaneously. These objects, whatever they were, had to be natural. But what natural object could pulse so precisely? The fastest spinning object known at the time was the Sun, which rotates once every 25 days. These objects were pulsing multiple times per second. The answer, when it finally emerged, was almost as strange as aliens: neutron stars. These are the collapsed cores of massive stars that have exploded as supernovae, compressed by gravity to densities so extreme that protons and electrons are crushed together to form neutrons. A neutron star with a mass 1.4 times that of our Sun, which has a diameter of 392 kilometers, is compressed into a sphere only 20 kilometers across, roughly the size of a city. A single teaspoon of neutron star material would weigh approximately 400 million tons, more than all the cars on Earth combined. The density reaches an almost incomprehensible 500 million metric tons per cubic centimeter. Imagine cramming all of humanity's 8 billion people into a sugar cube. Neutron stars spin rapidly because of conservation of angular momentum. As the core collapses from roughly 700,000 kilometers to just 20 kilometers in diameter, it spins faster, like a figure skater pulling in their arms. Some neutron stars rotate hundreds of times per second. They have incredibly strong magnetic fields, about 1 trillion times stronger than Earth's magnetic field of 50 microteslas. And these fields accelerate particles near the star's magnetic poles, causing them to emit beams of radio waves. As the neutron star rotates, these beams sweep across space like lighthouse beams. If Earth happens to be in the path of one of these beams, we detect a pulse each time the beam sweeps past us. These objects are called pulsars, pulsating stars. The discovery of pulsars opened a window into physics at its most extreme. Neutron stars represent matter compressed to the absolute limit before collapsing into a black hole. Their density is comparable to that of an atomic nucleus, as if you took all the empty space out of matter and packed the nucleons together as tightly as possible. The gravity at the surface of a neutron star is approximately 200 billion times stronger than Earth's gravity. If you could somehow stand on the surface, which you couldn't because you would be instantly crushed, you would weigh about 14 trillion kilograms, assuming you normally weigh 70 kilograms on Earth. But pulsars, as strange as they are, were just the beginning. In 1974, astronomers Russell Hulse and Joseph Taylor discovered something even more remarkable: a binary pulsar system, two neutron stars orbiting each other. This system, designated PSR B1916, consists of a pulsar with a period of 59 milliseconds orbiting a companion neutron star every 7.75 hours. The orbit is highly elliptical, and at its closest approach, the two neutron stars pass within 1.1 solar radii of each other, closer than the surface of the Sun if you placed one at its center. What made this system extraordinary was not just that it existed, but what it was doing. According to Einstein's general theory of relativity, accelerating massive objects should produce gravitational waves, ripples in the fabric of spacetime itself that propagate outward at the speed of light, traveling at exactly 299,792 kilometers per second. These gravitational waves carry energy away from the system, causing the orbit to slowly decay. The two neutron stars should be spiraling closer together, gradually but measurably. Hulse and Taylor monitored the binary pulsar for years, measuring the orbital period with extraordinary precision by timing the pulses from the pulsar. They found that the orbit was indeed decaying at exactly the rate predicted by general relativity. The two neutron stars were spiraling inward by about 3.5 millimeters per orbit, losing energy to gravitational waves radiating into space. This was the first indirect evidence that gravitational waves actually exist, confirming one of the most important predictions of Einstein's theory. Hulse and Taylor received the Nobel Prize in Physics in 1993 for this discovery. But the story of the binary pulsar raises a disturbing question. If the orbit is decaying, what happens eventually? The two neutron stars are spiraling closer together, orbiting faster and faster as they lose energy. In approximately 300 million years, they will merge in a catastrophic collision. When that happens, the merger will release more energy in a fraction of a second than our Sun will emit in its entire 10 billion year lifetime. The collision will produce a burst of gravitational waves so powerful that they will be detectable across the universe. It will also, almost certainly, produce something even stranger than a neutron star: a black hole. Black holes are regions of spacetime where gravity is so strong that nothing, not even light traveling at 299 to 792 kilometers per second, can escape. They are created when matter is compressed beyond even the density of a neutron star, when gravity overwhelms every known force and causes spacetime itself to collapse. The boundary of a black hole is called the event horizon, the point of no return. Anything that crosses the event horizon is lost forever, unable to communicate with the outside universe, doomed to fall inexorably toward the singularity at the center where density becomes infinite and the laws of physics as we understand them break down completely. Black holes sound like science fiction, like mathematical abstractions too strange to actually exist. Yet we have overwhelming evidence that they do exist and that they are common throughout the universe. The first strong evidence came in the 1970s from an object called Cygnus X1, a powerful X-ray source in the constellation Cygnus, located approximately 6,070 light-years from Earth. The X-rays appeared to come from a binary system where a visible blue supergiant star was orbiting something invisible, something compact but with a mass at least 10 times that of the Sun. The invisible companion was pulling material off the supergiant star, forming an accretion disk, a swirling disk of gas spiraling inward. As the gas spirals toward the compact object, friction and compression heat it to millions of degrees, hot enough to emit X-rays. But the compact object itself remains invisible. It emits no light of its own. The mass is too large to be a neutron star. Above about 3 solar masses, nothing can support matter against gravitational collapse. The only possibility is a black hole. We now know that Cygnus X1 contains a black hole with a mass of approximately 21 solar masses, formed from the collapse of a massive star that exploded as a supernova millions of years ago. The black hole itself is only about 124 kilometers in diameter, the size of its event horizon, but contains 21 times the mass of our Sun. It is so dense that if you replace the Sun with this black hole, its event horizon would fit comfortably inside Mercury's orbit, which extends 58 million kilometers from the Sun. But stellar mass black holes like Cygnus XE1, as bizarre as they are not the strangest black holes in the universe. That distinction belongs to the supermassive black holes that lurk at the centers of galaxies. In the 1970s and 1980s, astronomers began to realize that something strange was happening at the centers of many galaxies. Some galaxies had incredibly bright cores, so bright that they outshone the entire rest of the galaxy, billions of stars, from a region smaller than our solar system. These were the quasars that Jocelyn Bell had been searching for when she discovered pulsars. The energy output was staggering, up to 100 times the luminosity of the entire Milky Way galaxy, which radiates approximately 10 to 37 watts of power, emanating from a region just light hours or light days across. What could produce such enormous energy? Nuclear fusion, the process that powers stars, couldn't account for it. Chemical reactions certainly couldn't. The only viable explanation was gravitational energy from matter falling into a supermassive black hole, a black hole with a mass millions or billions of times that of the Sun. As matter spirals inward, it forms an accretion disk heated to millions of degrees, emitting enormous amounts of radiation across the electromagnetic spectrum. Some of this material is also ejected in powerful jets that stream away from the black hole at nearly the speed of light, extending for thousands or even millions of light years into intergalactic space. But did such objects really exist? Could black holes really grow to masses of millions or billions of solar masses? The evidence gradually became overwhelming. Astronomers studied the motion of stars and gas near the centers of galaxies. They found stars orbiting at incredible speeds, hundreds or thousands of kilometers per second, around invisible objects. By measuring these orbital velocities and applying Newton's laws of motion, they could calculate the mass of the invisible object. The numbers were staggering: millions of solar masses in some galaxies, billions in others. Our own Milky Way galaxy has a supermassive black hole at its center, designated Sagittarius A, pronounced Sagittarius A star. Astronomers have tracked individual stars orbiting this object for more than 20 years. One star, designated S2, has an orbital period of only 16 years, and at closest approach comes within 17 light hours of the black hole, closer than Uranus is to our Sun, traveling at speeds up to 7,950 kilometers per second, about 2.5% of the speed of light. From these observations, astronomers have calculated that Sagittarius AI has a mass of approximately 4.3 million solar masses, 4 million times the mass of the Sun, packed into a region smaller than Mercury's orbit. The event horizon of Sagittarius AI has a diameter of about 44 million kilometers, which sounds large until you realize it would fit comfortably inside Mercury's orbit around the Sun at 58 million kilometers. This object is so dense, so massive, that it holds an entire galaxy of 100 to 4 billion stars in its gravitational grip, yet it occupies a volume tiny compared to the galaxy itself. But even Sagittarius A is not the largest black hole we've discovered. That honor goes to ultramassive black holes found in some of the most distant and luminous quasars. The current record holder, designated TON 618, has a mass estimated at 66 billion solar masses, 66 billion times the mass of our Sun, collapsed into a black hole. The event horizon of this monster is about 1,300 astronomical units in diameter, 1,300 times the Earth-Sun distance of 150 million kilometers, which would extend well beyond the orbit of Pluto and into the outer reaches of our solar system. Yet even at this enormous size, the black hole is still infinitely dense at its core, still contains a singularity where the known laws of physics break down. These supermassive black holes raise profound questions. How did they form? How did they grow so large? A stellar mass black hole forms from the collapse of a massive star, but a star can only be so large. The most massive stars are only about 100 to 200 solar masses, and even these lose much of their mass through stellar winds before collapsing. How do you get from a 20 or 30 solar mass stellar black hole to a billion solar mass supermassive black hole? The answer appears to be feeding and merging. Black holes can grow by accreting matter from their surroundings, gas, dust, even entire stars that venture too close. They can also grow by merging with other black holes when galaxies collide. Galaxy collisions are common in the universe, and when two galaxies merge, their central black holes eventually merge as well, creating an even larger black hole. Over billions of years, through countless mergers and continuous accretion, supermassive black holes can grow to the enormous sizes we observe. But there's a problem with this explanation. We've found supermassive black holes in quasars that existed when the universe was less than 1 billion years old, less than 7% of its current age of 13.8 billion years. These black holes already had masses of millions, or even billions of solar masses. How did they grow so large so quickly? There hasn't been enough time for them to reach such enormous masses through normal accretion and merging. This is one of the great unsolved problems in astrophysics, the existence of supermassive black holes in the very early universe. Some astronomers propose that perhaps the first black holes didn't form from stars at all. Perhaps they formed directly from the collapse of enormous clouds of primordial gas in the early universe, creating seed black holes with masses of thousands or even hundreds of thousands of solar masses right from the start. These seeds could then grow through accretion to reach supermassive sizes relatively quickly. But we don't know if this actually happened. We've never directly observed the formation of such an object. The existence of black holes raises deeply unsettling questions about the nature of reality itself. What happens inside a black hole? What is the singularity at the center where density becomes infinite? Our current theories, general relativity and quantum mechanics, break down at the singularity. General relativity predicts that the singularity should exist, but quantum mechanics suggests that infinite densities are impossible. These two pillars of modern physics are incompatible at the extreme conditions inside a black hole. Some physicists speculate that black holes might be tunnels to other parts of the universe, or even to other universes entirely. These are called wormholes, hypothetical shortcuts through spacetime. But there's no evidence that wormholes actually exist, and the mathematics suggests that if they do exist, they would be catastrophically unstable, collapsing almost instantly unless supported by exotic matter with bizarre properties we've never observed. Other physicists, following Stephen Hawking's groundbreaking work in the 1970s, believe that black holes slowly evaporate through quantum effects, emitting what's now called Hawking radiation. If this is correct, then black holes are not truly eternal. They slowly lose mass over timescales of 10^67 years for stellar mass black holes and 10^100 years for supermassive ones. Eventually, every black hole in the universe will evaporate, leaving behind only radiation. But this raises its own puzzle. If information falls into a black hole and the black hole eventually evaporates completely, where does the information go? Is it destroyed? The laws of quantum mechanics suggest that information cannot be destroyed, leading to what's called the black hole information paradox, still unresolved after decades of debate. Perhaps the strangest aspect of black holes is what happens to time near them. According to general relativity, time passes more slowly in strong gravitational fields. Near the event horizon of a black hole, time dilation becomes extreme. If you could watch someone fall into a black hole from a safe distance, you would see them slow down as they approach the event horizon. They would appear to freeze, never quite crossing the horizon, their image becoming increasingly redshifted until they faded from view. To them, subjectively, they would cross the horizon normally, experiencing nothing special at that moment. But to you watching from outside, they would appear frozen at the edge of the black hole forever. This time, dilation isn't just theoretical. It's measurable and has been confirmed countless times. GPS satellites must account for time dilation due to Earth's gravitational field and their orbital velocity, or they would accumulate errors of several kilometers per day. Time, actually, passes about 38 microseconds per day, faster for GPS satellites than for clocks on Earth's surface. Near a black hole, these effects become not microseconds, but seconds, minutes, or years. Imagine a pair of identical twins. One remains on Earth, while the other journeys in a spacecraft to orbit close to the event horizon of a black hole, spending what feels like 1 hour there before returning. Due to time dilation, thousands or even millions of years might pass on Earth, while only an hour passes for the traveler. The twin who visited the black hole would return to find their sibling long dead, human civilization perhaps vanished, the Earth unrecognizably changed. They would have effectively traveled into Earth's future. This is not science fiction. This is a consequence of Einstein's equations, confirmed by every experiment we've ever performed. Black holes are time machines of a sort, allowing travel into the future but never into the past. The gravitational field warps spacetime itself, stretching the very fabric of reality. But black holes, as strange as they are not the only extreme objects in the universe. Neutron stars, too, have properties that challenge our understanding. In 2004, astronomers detected a massive burst of radiation from a neutron star designated SGR 1806-20, located about 50,000 light-years away on the far side of our galaxy. In 1/10 of a second, this object released more energy than the Sun emits in 150,000 years. The radiation was so intense that it affected Earth's upper atmosphere, despite being halfway across the galaxy. SGR 1806-20 is what's called a magnetar, a neutron star with a magnetic field about 1,000 times stronger than a typical pulsar, making it one of the strongest magnetic fields known in the universe. The magnetic field of a magnetar is approximately 10·11 teslas, or 100 billion teslas. For comparison, Earth's magnetic field is about 0.05 teslas. A typical refrigerator magnet is about 1 teslas. An MRI machine uses fields of 1 to 3 teslas. The magnetic field of a magnetar is so strong that it affects the very structure of space-time, distorting atoms into elongated needle shapes, making chemistry as we know it impossible. If you brought a magnetar's magnetic field close to Earth, say within half the distance to the Moon, it would strip electrons from atoms, destroying molecular bonds, effectively disintegrating any matter it encountered. The magnetic field itself contains so much energy that sudden rearrangements of the field lines, analogous to earthquakes but occurring in the star's crust, can trigger massive explosions called starquakes, releasing as much energy in a fraction of a second as the Sun emits in millennia. How do magnetars form? The most likely explanation is that they're created in supernova explosions of particularly massive stars, possibly stars that were rotating rapidly before they collapsed. The rapid rotation combined with the collapse might amplify the magnetic field through a dynamo effect, concentrating and intensifying the field to extreme levels. But we don't fully understand the process. Magnetars are rare. We've discovered only about 30 in our galaxy, and we've never observed one being born. Magnetars challenge our understanding of physics in extreme conditions. The magnetic fields are so strong that they enter a regime where quantum effects of the electromagnetic field itself become important, where the vacuum of space itself can be polarized by the field. This is physics at the absolute frontier of what we can understand theoretically, let alone observe. Yet, as strange as neutron stars and black holes are, at least they're made of matter, or in the case of black holes, represent the ultimate fate of matter. But space contains stranger things still, objects and phenomena that don't fit into our categories, that challenge our very understanding of what exists means. In 1933, astronomer Fritz Zwicky was studying the Coma Cluster, a group of more than 1,000 galaxies about 320 million light-years away. He measured how fast individual galaxies were moving within the cluster by observing the Doppler shifts of their spectral lines. What he found was deeply puzzling. The galaxies were moving much too fast. According to Newton's law of gravitation, the cluster should fly apart given the velocities he measured, unless there was much more mass holding it together gravitationally than he could see in the visible galaxies. Zwicky calculated that the cluster needed about 400 times more mass than could be accounted for by visible matter, the stars and gas he could observe. He called this unseen mass dunkle Materie, German for dark matter. Most astronomers dismissed his results, assuming he'd made an error somewhere in his calculations or observations. But in the 1970s, astronomer Vera Rubin made a similar discovery while studying the rotation curves of spiral galaxies. She measured how fast stars were orbiting at different distances from the galactic center. Based on the visible matter, stars and gas, the orbital speeds should decrease with distance from the center, just as planets farther from the sun orbit more slowly. But that's not what Rubin found. The stars at the edges of galaxies were orbiting just as fast as stars closer to the center, sometimes even faster. This made no sense according to Newtonian gravity unless there was much more mass in these galaxies than we could see. Rubin calculated that galaxies must contain about 5 to 10 times more dark matter than visible matter. The visible galaxy, all the stars we can see, is just the tip of the iceberg, embedded in a much larger halo of invisible dark matter. Today, we have overwhelming evidence for dark matter from multiple independent lines of observation: galaxy rotation curves, gravitational lensing, the cosmic microwave background, large-scale structure formation, and more. All the evidence points to the same conclusion. Approximately 85% of the matter in the universe is dark matter. Only 15% is the ordinary matter, protons, neutrons, electrons, that makes up stars, planets, and us. But what is dark matter? We don't know. It doesn't emit light, doesn't absorb light, doesn't reflect light. It apparently interacts with ordinary matter only through gravity. It passes through ordinary matter almost as if the matter weren't there. You have dark matter particles passing through your body right now, trillions of them every second, and you cannot feel them at all. The leading candidates are called weakly interacting massive particles, or WIMPs, hypothetical particles predicted by extensions of the standard model of particle physics. Physicists have built extraordinarily sensitive detectors deep underground, shielded from cosmic rays, looking for the rare occasions when a WIMP might collide with an atomic nucleus. After decades of searching, using detectors that can sense the recoil of a nucleus hit by a single particle, we have found nothing definitive. Other candidates include axions, sterile neutrinos, and even primordial black holes formed in the very early universe. But we simply don't know. Dark matter is all around us, in us, passing through us, holding galaxies together, determining the large-scale structure of the universe, yet we cannot see it or touch it or capture it. It is literally invisible matter, detectable only through its gravitational effects. This is deeply unsettling. It means that most of the universe is made of something we've never directly detected, something that might be fundamentally different from anything we've ever experienced. We live in a universe where 85% of the matter is unknown, mysterious, perhaps unknowable. Yet as strange as dark matter is, there's something even stranger: dark energy. In 1998, two teams of astronomers were measuring distances to distant supernova explosions, trying to determine how much the expansion of the universe had been slowing down over cosmic time. Everyone expected to find that gravity was causing the expansion to decelerate, gradually slowing over billions of years. Instead, they found the opposite. The expansion is accelerating. The universe is expanding faster today than it was a billion years ago. This discovery shocked the astronomy community. What could cause the expansion to accelerate? According to general relativity, you need some form of energy with negative pressure, essentially a kind of anti-gravity, to drive acceleration. This energy appears to be a property of empty space itself, present everywhere, constant in density even as the universe expands. Cosmologists call it dark energy, though it's not really energy in the usual sense, and it's not particularly dark. It's more like a property of spacetime itself, a cosmic pressure that causes space to expand. And it's not a small effect. Measurements suggest that dark energy comprises about 68% of the total energy content of the universe. Think about that. 68% dark energy, 27% dark matter, only 5% ordinary matter. Everything we can see and touch and detect directly, all the stars in all the galaxies, all the planets, all the gas and dust, everything made of atoms, is only 5% of what exists. 95% of the universe is mysterious, made of things we've never directly detected, whose fundamental nature we don't understand. Dark energy is perhaps the deepest mystery in modern cosmology. We don't know what it is, why it exists, or why it has the density it does. Some physicists think it might be related to the quantum vacuum, the seething sea of virtual particles that quantum mechanics predicts should exist even in empty space. But when you calculate what the vacuum energy should be based on particle physics, you get a number that's wrong by a factor of 10 to 20, the worst prediction in the history of science. Others think dark energy might be a new field pervading all of space, something like the Higgs field but operating on cosmic scales. Still others speculate that we might need to modify Einstein's general relativity on the largest scales, that gravity might work differently across billions of light years than it does in our solar system. We simply don't know. And this is terrifying in a way, because dark energy determines the ultimate fate of the universe. If dark energy remains constant, the universe will expand forever, eventually reaching heat death. If dark energy increases, we might face a big rip, where the universe literally tears itself apart. If dark energy somehow decreases, gravity might win and the universe could recollapse in a big crunch. The fate of everything, every star, every galaxy, every planet, every possible future civilization depends on the behavior of this mysterious dark energy that we don't understand. We are passengers on a cosmic ship, and we don't know where we're going. These are the strangest things we've discovered in space. Neutron stars compressed to impossible densities of 500 million metric tons per cubic centimeter. Black holes where spacetime collapses and time itself breaks down. Dark matter that is invisible yet holds galaxies together. Dark energy that pushes the universe apart and determines its ultimate fate. These aren't speculative fictions or mathematical fantasies. They are real, observed phenomena that challenge our understanding of physics at its most fundamental level. And yet, as strange as these objects are, they may only be the beginning. In the deep darkness of space, in regions we haven't yet observed, phenomena we haven't yet imagined might be waiting to be discovered. The universe has surprised us repeatedly with objects stranger than we thought possible. What other mysteries are hidden in the cosmic depths, waiting for the right telescope, the right observation, the right insight to bring them into view? The night sky looks peaceful, unchanging, eternal. But beneath that peaceful facade, the universe is far stranger than we ever imagined. Neutron stars pulse like cosmic lighthouses. Black holes tear space-time apart. Invisible matter holds everything together, while invisible energy pushes everything apart. We live in a universe that is 95% mystery, where the strangest things we've discovered may only hint at stranger things still waiting to be found. The telescope sits in orbit above Earth's atmosphere, shielded from the distorting effects of air and light pollution. It is not looking in visible light like our eyes do, but in X-rays, high-energy radiation that cannot penetrate our atmosphere, radiation emitted only by the most violent and extreme processes in the universe. X-rays come from gas heated to millions of degrees, from matter spiraling into black holes, from the remnants of exploded stars. The telescope's detectors are counting photons, building up images over hours or days, revealing a universe invisible to our eyes. In these X-ray images, the cosmos looks alien, threatening, violent. Where visible light shows peaceful spiral galaxies, X-rays reveal chaos, supermassive black holes devouring matter, neutron stars colliding, shockwaves from explosions that dwarf anything we can imagine. But among all the violence, among all the extreme phenomena, there are patterns that don't make sense, signals that shouldn't be there. In 2014, astronomers detected something peculiar in the X-ray data from galaxy clusters. It was a faint emission line, a spike in X-ray intensity at a very specific energy. The line appeared at the same energy in multiple different clusters, suggesting it was real rather than instrumental error. But there was a problem. No known atomic transition produces an X-ray line at that energy. It didn't match hydrogen, helium, oxygen, iron, or any other element. It was as if the X-rays were coming from atoms that don't exist. The signal was weak, barely above the noise, but it was consistent. Different telescopes, different galaxy clusters, all showed the same mysterious line. Some physicists proposed an intriguing explanation. What if the line was produced by dark matter? We know dark matter exists from gravitational effects, but we don't know what it is. Most models assume dark matter particles are stable, that they simply exist unchanged for billions of years. But what if some dark matter particles decay, very rarely, into ordinary matter and radiation? One candidate for dark matter is called a sterile neutrino, a hypothetical particle that doesn't interact through any of the fundamental forces except gravity. If sterile neutrinos with a specific mass decay, they would produce X-rays at exactly the energy observed. Could this emission line be our first direct detection of dark matter, the first time we've actually seen dark matter do something other than pull gravitationally? The possibility is tantalizing, but the signal is weak and controversial. Other explanations exist. Perhaps it's from some unexpected atomic transition or from a new astrophysical process we haven't considered. The mystery remains unsolved. Dark matter continues to evade direct detection despite decades of effort. The detectors built to catch it are marvels of technology, buried deep underground in mines to shield them from cosmic ray interference, cooled to near absolute zero to minimize thermal noise, sensitive enough to detect the recoil of a single atomic nucleus struck by a passing particle. Some detectors use tanks of liquid xenon. Others use crystals of germanium or silicon. All are waiting for the telltale sign of a dark matter particle colliding with an atom. So far, nothing. Or rather, nothing conclusive. There have been hints, tantalizing possible signals that appear and then disappear when you gather more data or look more carefully. False alarms, statistical fluctuations, unexplained backgrounds. The dark matter particles, if they exist, are either more elusive than we thought or we're looking in the wrong way. This is frustrating because we know dark matter is there. We can see its effects. Gravitational lensing, where the gravity of massive objects bends light from more distant objects, reveals dark matter's presence. The famous bullet cluster, two galaxy clusters that collided and passed through each other, shows this clearly. The visible matter, hot gas, was stripped away by the collision and left behind, glowing in X-rays. But the gravitational lensing shows that most of the mass continued moving with the galaxies themselves. The dark matter passed through the collision like a ghost, unaffected by the electromagnetic forces that slowed the gas. We can map where dark matter's in the universe, can see how it's distributed in halos around galaxies and in enormous filaments connecting galaxy clusters. We just can't catch it, can't isolate a single particle and study its properties. It's like trying to study something that can only be seen by its shadow, never directly. But dark matter, at least, is matter. It has mass, it gravitates, it clumps together. Dark energy is even more perplexing because it doesn't clump. It appears to be perfectly uniform, the same everywhere, and its density doesn't change as the universe expands. This is deeply strange. When the universe expands, the density of ordinary matter decreases. The same amount of matter in a larger volume means lower density. The density of radiation decreases even faster, but dark energy's density stays constant. This means that as the universe expands, there's more dark energy, because there's more space, and dark energy is a property of space itself. This has profound implications for the future. Right now, matter and dark energy are roughly comparable in their influence on cosmic dynamics. But as the universe continues expanding, matter becomes more dilute while dark energy remains constant. Eventually, dark energy will dominate completely. The expansion will accelerate faster and faster, driven by the relentless pressure of dark energy. Distant galaxies will be pushed away from us so quickly that even light cannot overcome the expansion. They will disappear beyond our cosmic horizon, their light redshifted into oblivion. Eventually, only our local group of gravitationally bound galaxies will remain visible. The rest of the universe will vanish, and future astronomers billions of years from now will have no evidence that the universe was once filled with galaxies. No evidence of the Big Bang, no way to reconstruct the cosmic history we've been fortunate enough to observe. But dark energy's mysteries don't end with cosmic acceleration. Some physicists worry that dark energy might not remain constant. What if it's changing, slowly increasing, or decreasing? If it increases beyond a certain threshold, the acceleration could become catastrophic. Space would expand so rapidly that it would overcome the forces holding matter together. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems, then planets, then atoms themselves. This scenario is called the Big Rip, and it would represent the ultimate destruction of all structure in the universe. We don't know if this will happen because we don't know what dark energy is or how it behaves. We can measure that it exists, that it's causing acceleration, but we can't predict its future behavior without understanding its fundamental nature. It's like being in a car that's accelerating and not knowing whether there's a driver at the wheel or if the accelerator is stuck. The mystery of dark energy connects to another puzzle. Why does the universe appear fine-tuned for complexity? The density of dark energy could, in principle, be much larger or much smaller than it is. If it were much larger, the universe would have expanded so rapidly that galaxies could never form. If it were much smaller, or zero, gravity would dominate, and the universe might have collapsed back on itself. The observed value seems to be in a narrow range that allows for the existence of stars, galaxies, and ultimately life. This apparent fine-tuning troubles physicists. Is it just luck? Is there some deeper principle that requires dark energy to have this value? Or are we misunderstanding something fundamental about how the universe works? Some invoke the anthropic principle. We observe this value because only in a universe with this value could observers exist. But this explanation doesn't satisfy everyone. It feels like giving up on finding a deeper answer. While cosmologists grapple with dark energy, astronomers studying individual objects have found their own share of mysteries. In 2017, an observatory in Hawaii detected something extraordinary, an object moving through our solar system on a trajectory that came from interstellar space. This was the first interstellar object ever observed passing through our cosmic neighborhood. They named it Oumuamua, Hawaiian, for scout or messenger from afar. At first, it seemed like an asteroid or comet from another star system, ejected by gravitational interactions and now drifting through the galaxy. But as astronomers gathered more data, Oumuamua revealed itself to be deeply strange. Its shape was bizarre, highly elongated, roughly 10 times longer than it was wide. Nothing in our solar system looks like this. Asteroids and comets are generally round or potato-shaped, not elongated cigars. Its rotation was odd, too, tumbling in a complex pattern unlike the simple rotation of typical asteroids. But the strangest thing was its motion. As Oumuamua left the inner solar system, it accelerated slightly, as if pushed by an unseen force. Comets do this. They're pushed by jets of gas as ice evaporates from their surfaces. But Oumuamua showed no signs of being a comet, no tail, no coma, no detected outgassing. Yet, it was accelerating. Various explanations were proposed. Maybe it was a comet made of pure nitrogen ice, which would evaporate without producing a visible tail. Maybe it was unusually porous, like a fractal dust aggregate, which could produce thrust without visible outgassing. Maybe the acceleration was from outgassing we simply couldn't detect with our instruments. One Harvard astronomer, Avi Loeb, proposed a more radical explanation. What if Oumuamua was artificial? What if it was a light sail, a thin reflective sheet pushed by the pressure of sunlight, built by an alien civilization? Light sails are a real technology. We've built tiny ones on Earth and proposed using them for interstellar probes. An alien civilization might use them for exploration, sending thousands or millions of probes through the galaxy, most never encountering anything interesting, but a few, perhaps finding planetary systems like ours. The scientific community largely rejected this hypothesis, arguing that natural explanations were more plausible and that extraordinary claims require extraordinary evidence. But no natural explanation perfectly fits all the observations. Oumuamua remains puzzling, and we'll likely never know its true nature because it's now too far away to study further, receding into interstellar space at about 30 kilometers per second. Oumuamua reminds us that space contains objects we've never seen before, perhaps objects we've never imagined. It came from another star system, from conditions and processes potentially very different from those in our solar system. If one interstellar object can pass through, there must be countless others. Most go undetected, slipping through the solar system unseen. What else might be out there, drifting between the stars? The discovery of interstellar objects opens new questions about what exists in the vast spaces between stars. We tend to think of interstellar space as empty, but it's not quite empty. It contains gas and dust, though incredibly diffuse, about 1 atom per cubic centimeter on average, a vacuum far better than anything we can create in laboratories. There are also magnetic fields threading through interstellar space, and perhaps other things we haven't detected. Some astronomers speculate about rogue planets, worlds ejected from their parent star systems during formation and now drifting alone through the galaxy. Simulations suggest there might be billions of rogue planets in our galaxy, possibly outnumbering planets orbiting stars. These worlds would be dark and cold, frozen in perpetual night, but they might have internal heat from radioactive decay or tidal forces if they have large moons. Could life exist on such a world? Could a civilization develop in complete darkness, never seeing stars, never knowing that the universe extends beyond their frozen planet? We've also found strange objects within our own solar system that challenge our understanding. The outer solar system, beyond Neptune's orbit, contains thousands of small, icy bodies. Most follow predictable orbits, but a few have orbits so extreme they're difficult to explain. Some have orbits tilted at high angles to the plane of the solar system. Some have orbits so elongated that they venture hundreds of times farther from the Sun than Earth. The strangest have orbits that seem to point in similar directions, as if something massive is gravitationally hurting them. Some astronomers have proposed that a large planet, perhaps several times Earth's mass, might exist in the distant outer solar system, too far away and too faint to have been detected yet. This hypothetical Planet 9 would orbit the Sun at distances of 400 to 800 times Earth's distance, taking 10,000 to 20,000 years to complete one orbit. Searches for Planet 9 have found nothing so far. Maybe it doesn't exist and the orbital patterns are just coincidence. Or maybe it's out there, lurking in the darkness, waiting to be found. The solar system, after billions of years of observation, still holds secrets. But perhaps the strangest objects in space are those we cannot see at all, not even with our most sophisticated instruments. Theoretical physics predicts the possible existence of objects so bizarre that they sound like fantasy. Cosmic strings, domain walls, magnetic monopoles, cue balls. These are hypothetical remnants from the extremely early universe, fractions of a second after the Big Bang, when conditions were so extreme that exotic states of matter might have briefly existed. Cosmic strings, if they exist, would be defects in spacetime itself, one-dimensional objects thinner than a proton but potentially stretching across the universe, with masses so enormous that a piece the length of Earth's orbit around the Sun would outweigh the Sun. They would gravitationally lens light, creating distinctive double images of distant objects. So far, searches have found nothing, but the absence of evidence doesn't prove cosmic strings don't exist. They might simply be very rare. Magnetic monopoles are hypothetical particles that have only a north pole or only a south pole, unlike ordinary magnets which always have both. They're predicted by certain grand unified theories of particle physics. If they were created in the Big Bang, they should still exist, incredibly rare but present. Astronomers have looked for their distinctive signatures and found nothing. Maybe they don't exist, or maybe they're so rare that we've simply been unlucky. These exotic objects might seem like pure speculation, but they emerge from serious physics, from our best attempts to understand the fundamental laws governing reality. The early universe was a laboratory of extreme conditions we can never recreate on Earth. If these objects were created then, they should still exist somewhere, fossils from cosmic dawn. Even more speculative are objects related to string theory and higher dimensions. String theory proposes that the fundamental constituents of reality are not point particles, but tiny vibrating strings, and that the universe has more than the three spatial dimensions we perceive. The extra dimensions are supposedly curled up very small, too small to detect directly. But some versions of string theory predict objects called brains, higher dimensional surfaces in this extended space. Our entire universe might be a three-dimensional brain floating in a higher dimensional space. If brains exist, could we detect them? Could our universe collide with another brain? Some physicists have speculated that dark energy might be a force reaching us from another brain, or that gravity is weaker than other forces because it leaks into extra dimensions. These ideas are highly speculative and currently untestable, but they represent physicists' attempts to understand the deepest questions about reality. The search for strange objects in space is also a search for signals from extraterrestrial intelligence. If advanced civilizations exist elsewhere in the universe, they might construct objects or structures we could detect. A civilization with technology far beyond ours might build Dyson spheres, enormous structures surrounding their star to capture all its energy output. Such structures would absorb visible light and re-emit it as infrared radiation, creating a distinctive signature we could detect. Astronomers have searched for such signatures, looking for stars that seem too bright in infrared and too dim in visible light. They've found some candidates that might be Dyson spheres, but all have natural explanations involving dust or other phenomena. No smoking gun, no clear evidence of artificial structures. Similarly, searches for alien radio signals have continued for decades. The SETI program scans the sky looking for narrow-band radio signals that couldn't be produced naturally, signals that would indicate someone is broadcasting. Despite monitoring millions of radio frequencies and thousands of stars, SETI has found nothing conclusive. In 2017, a strange radio signal called the WOW signal was briefly thought to be from aliens. It was detected once, was incredibly strong, and had all the characteristics of an artificial signal. But it was never detected again, despite repeated observations of the same region of sky. Was it a glitch? A terrestrial interference? An actual alien signal that was broadcast only once? We'll likely never know. More recently, astronomers have detected fast radio bursts, or FRBs, intense pulses of radio waves that last only milliseconds but release enormous amounts of energy, sometimes as much energy in a millisecond as the sun emits in days. These bursts come from distant galaxies, billions of light years away. Most FRBs occur once and are never seen again, but a few repeat at irregular intervals. The origin of FRBs is unknown. They might be caused by magnetars, by colliding neutron stars, by black holes eating neutron stars, or by some other extreme astrophysical process we haven't imagined. When FRBs were first discovered, some speculated they might be alien signals, perhaps energy beams used to propel spacecraft, with Earth accidentally catching the beam. But most astronomers believe they're natural phenomena. Still, we don't know for certain. The more we study the universe, the more we realize how much we don't understand. Every answer generates new questions. We discovered pulsars and found neutron stars. Then we found magnetars and realized neutron stars are stranger than we thought. We discovered black holes and found they're common. Then we found supermassive black holes and realized they're even stranger than stellar ones. We discovered dark matter and found it comprises most of the matter in the universe. Then we discovered dark energy and found it comprises even more of the universe's content. What will we discover next? What lies waiting in the data from our telescopes, in observations not yet made, in phenomena not yet imagined? The universe has consistently proven stranger than our theories predict. Every time we think we understand the basics, reality surprises us. Perhaps there are phenomena we cannot detect with current technology, objects or entities that interact with ordinary matter so weakly that we've never noticed them. Perhaps there are forms of matter or energy that don't produce any electromagnetic radiation, that don't gravitationally lens light, that leave no trace except through subtle effects we haven't learned to recognize. Or perhaps the strangest things in space are not objects at all but phenomena, processes that violate our intuitions about how the universe works. Quantum mechanics already tells us that reality at the smallest scales is profoundly weird, with particles existing in multiple states simultaneously until observed, with entanglement allowing correlations between distant particles that Einstein called spooky action at a distance. Does quantum weirdness extend to cosmic scales? Some physicists think it might. The measurement problem in quantum mechanics, the question of how and when quantum systems collapse from superpositions to definite states, becomes particularly acute when applied to the entire universe. If the universe itself is a quantum system, what does it mean for it to be in a superposition? Who or what observes it to make it real? These questions venture into philosophy as much as physics, but they're motivated by real mysteries in our understanding of reality. The strange objects we find in space, neutron stars, black holes, dark matter, dark energy, are symptoms of a deeper strangeness, hints that the universe operates according to principles we haven't fully grasped. Perhaps the most unsettling possibility is that we're fundamentally limited in what we can understand. Our brains evolved to survive on Earth, to hunt and gather and navigate social relationships. They did not evolve to comprehend quantum mechanics or general relativity or cosmic inflation. The fact that we can understand as much as we do is remarkable, perhaps miraculous. But there might be aspects of reality that are simply beyond our cognitive capacity, truths about the universe that we can never grasp no matter how long we study or how sophisticated our instruments become. This is a humbling thought. We've made extraordinary progress in understanding the universe, mapping its contents and history with increasing precision. But the more we learn, the more we realize how much remains mysterious. The strange objects we've discovered, pulsars, black holes, dark matter, dark energy, interstellar visitors, unexplained signals, are windows into a cosmos far stranger than common sense suggests, a universe that refuses to conform to our expectations. And somewhere in that strange universe, there may be things stranger still, objects we haven't detected because we don't know how to look for them. Phenomena that don't fit into our categories of matter and energy, perhaps even civilizations far advanced beyond us, with technologies we would struggle to recognize as technology, who see aspects of the universe invisible to us. The search continues. New telescopes are being built, new detectors designed, new theories developed. Each discovery answers some questions and raises others. The strange things we've found in space are not endpoints, but waypoints on a journey of understanding that may never be complete. The universe is vast, ancient, and full of mysteries. We've barely begun to explore it. There is a moment, deep in the night, when you look up at the stars and feel the weight of cosmic time pressing down on you. Those points of light are not what they seem. They are not fixed, eternal, unchanging. They are burning, evolving, dying. Some of the stars you see have already exploded, their light still traveling toward us, carrying the image of something that no longer exists. We are looking at ghosts, at echoes from the past, at a universe that has already moved on. In 2006, astronomers pointed the Hubble Space Telescope at a distant galaxy and watched a star die. Not just any star, but one of the most massive stars known, a behemoth with a mass perhaps 100 times that of our Sun. These hypergiant stars are incredibly rare and incredibly unstable. They burn so hot and so bright that radiation pressure from their cores pushes outward with nearly enough force to tear the star apart. They live fast and die spectacularly. This particular star, in a galaxy some distance away, began to brighten. Over a period of months, it increased in luminosity, not explosively as in a supernova, but steadily, building toward something. Astronomers watched, puzzled. The brightening continued. The star was pumping out more energy than it should be able to sustain. Then something extraordinary happened. The star simply vanished. Not exploded, vanished. One moment it was there, incredibly bright, radiating enormous amounts of energy. The next moment, nothing. No supernova, no explosion, no expanding shell of debris. The star was gone, leaving behind only darkness. Astronomers searched for remnants, for any sign of what had happened. They found nothing. The star had disappeared as completely as if it had never existed. The most likely explanation is chilling. The star collapsed directly into a black hole without exploding. Normally, when a massive star dies, it explodes in a supernova, blowing off its outer layers while the core collapses. But if a star is massive enough, the collapse might happen so quickly and completely that nothing escapes. No explosion, no supernova, no final blaze of glory. The star simply falls into itself, crossing its own event horizon, disappearing from the universe. It becomes a black hole in silence, leaving no trace except for a sudden absence of light. This is called a failed supernova, and it represents one of the most direct ways we might observe a black hole forming. But it's deeply unsettling. Stars are supposed to explode when they die. That's how they enrich the universe with heavy elements, how they spread the building blocks of planets and life across space. A failed supernova keeps all that material locked away forever, lost behind an event horizon, contributing nothing to the cosmic chemical evolution. It's a death that erases rather than creates. The discovery suggests that black holes might form more commonly than we thought. Perhaps many massive stars undergo failed supernovae, silently collapsing without fanfare. If so, there might be more stellar mass black holes in the galaxy than current estimates suggest, and these black holes would be especially difficult to detect because they formed without leaving behind the remnants and neutron stars that make other stellar deaths observable. Failed supernovae are just one example of cosmic phenomena that don't behave as our theories predict. Another mystery emerged in the early 2000s when astronomers began surveying distant supernovae more carefully. Type IEA supernovae, remember, are used as standard candles to measure cosmic distances because they all reach approximately the same peak brightness. But when astronomers looked at their data more carefully, they found something odd. The supernovae were slightly too dim, as if something was absorbing or scattering their light on the way to us. At first, astronomers thought this might be dust in intergalactic space. Dust absorbs and scatters light, making distant objects appear dimmer and redder. But the dimming didn't show the reddening expected from dust. The spectrum looked wrong. Moreover, the effect was the same in all directions, which seemed unlikely if it were caused by randomly distributed dust. The phenomenon remained unexplained for years. Some astronomers proposed exotic explanations. Perhaps light loses energy as it travels across cosmic distances through some unknown mechanism. Perhaps photons decay or transform into something else over billions of years. Perhaps there's some fundamental property of light we don't understand. But these explanations required new physics, violations of established principles. The scientific community was understandably skeptical. More recent observations suggest the dimming might be related to how we're measuring supernova distances and accounting for cosmic expansion. Perhaps there are subtle systematic errors in our standard candle calibrations. Or perhaps the dimming is real, but caused by something more mundane, like previously unaccounted for populations of faint galaxies between us and the supernovae. The mystery isn't fully resolved, but it's a reminder that cosmic observations are rarely straightforward. Light travels billions of years across an evolving universe, and many things can happen along the way. While studying supernovae, astronomers have also found objects that shouldn't exist according to our understanding of stellar evolution. In 2014, a particularly bright supernova was detected in a distant galaxy. It was incredibly luminous, far brighter than any supernova should be. Astronomers initially thought it might be a superluminous supernova, a rare type caused by extremely massive stars. But as they gathered more data, the object became stranger. It didn't fade like a supernova should. Supernovae brighten quickly, reach peak luminosity, then fade over weeks or months as the expanding debris cools and becomes transparent. But this object stayed bright for years. It would dim slightly, then brighten again, then dim in an irregular pattern. It was as if the explosion kept restarting, as if something was continuously pumping energy into the system. The object was designated A Assassin 15Elch, and it became one of the most luminous and longest-lasting stellar explosions ever observed. Various explanations were proposed. Perhaps it wasn't a supernova at all, but a star being tidally disrupted by a massive black hole, torn apart by gravity and consumed over an extended period. Perhaps it was a magnetar, a neutron star with an extraordinarily strong magnetic field, converting magnetic energy into radiation. Perhaps it was something entirely new, a type of explosion not accounted for in our models. Years later, SN 15LH is still not fully explained. It may have been a tidal disruption event, but some aspects of its behavior don't quite fit that model either. It exists in an observational limbo, too strange to categorize definitively. And it's not alone. Astronomers have found several similar objects, explosions that don't behave like any known type of supernova, that persist far longer than they should, that challenge our understanding of how stars die. These objects hint at phenomena occurring at the extremes of stellar death, in conditions we can barely model theoretically and can't replicate experimentally. When a star much more massive than the Sun collapses, the densities and temperatures reached are so extreme that our understanding of nuclear physics becomes uncertain. New particles might be created. Exotic states of matter might briefly exist. We're extrapolating our physics far beyond where we've tested it, and perhaps we shouldn't be surprised when reality deviates from our predictions. Even more mysterious are gamma-ray bursts, or GRBs. These are the most energetic explosions known in the universe, brief flashes of gamma rays that release more energy in seconds than the sun will emit in its entire lifetime. They come from random directions in the sky, occurring roughly once per day somewhere in the observable universe. For the brief duration of the burst, a GRB can outshine every other gamma-ray source in the sky combined. The first GRBs were detected accidentally in the late 1960s by military satellites designed to watch for nuclear weapons tests. The satellites detected bursts of gamma rays coming from space, not from Earth. The military kept the discovery classified for years, unsure what they were seeing. When the data was finally declassified and published in 1973, astronomers were baffled. What could produce such intense bursts of gamma rays? For decades, the origin of GRBs remained mysterious. They seemed to come from far away, but without knowing their distance, astronomers couldn't determine their energy output. Were they nearby but weak, or distant but incredibly powerful? The bursts lasted only seconds, so they had to come from something compact and violent. But what? The breakthrough came in 1997 when astronomers finally managed to detect the afterglow of a GRB in visible light and measure its distance. The burst came from a galaxy billions of light years away. This meant GRBs were releasing enormous amounts of energy, making them the most powerful explosions in the universe. But what could cause such an explosion? The current understanding is that long-duration GRBs, lasting more than 2 seconds, are caused by hypernovae, the deaths of extremely massive stars that collapse to form black holes. As the core collapses, it forms an accretion disk around the newborn black hole. Energy extracted from this system drives jets of material outward at nearly the speed of light. If Earth happens to lie along the axis of one of these jets, we see a GRB. It's like looking down the barrel of a cosmic gun at the moment it fires. Short-duration GRBs, lasting less than 2 seconds, are thought to come from colliding neutron stars. When two neutron stars in a binary system spiral together and merge, they release enormous amounts of energy in gravitational waves and gamma rays. The merger might produce a black hole, or it might produce a hypermassive neutron star that exists briefly before collapsing. Either way, the collision generates a short, intense burst of gamma rays. In 2017, astronomers detected both gravitational waves and gamma rays from a neutron star merger, confirming that short GRBs are indeed caused by such collisions. It was a triumph of multi-messenger astronomy, observing the same event with completely different types of signals. The gravitational waves told us about the collision dynamics, while the gamma rays told us about the electromagnetic emission. Together, they painted a complete picture of one of the universe's most violent events. But GRBs raise a disturbing possibility. If a GRB occurred in our galaxy pointed at Earth, it would be catastrophic. The gamma rays would strip away our ozone layer within seconds, exposing the surface to lethal levels of ultraviolet radiation. They would trigger chemical reactions in the atmosphere, producing nitrogen oxides that would further destroy ozone and create a brownish haze. The radiation would damage DNA in living organisms, potentially causing a mass extinction. Some paleontologists have speculated that past mass extinctions might have been triggered by nearby GRBs. The Ordovician extinction, one of the 5 major mass extinctions in Earth's history, occurred suddenly without obvious cause. Could a GRB have been responsible? We have no direct evidence, but it's a possibility. The universe is a dangerous place, filled with violent phenomena that could sterilize a planet from thousands of light years away. Fortunately, GRBs are rare in any given galaxy, and the odds of one pointing at Earth are very small. The beam is narrow, perhaps only a few degrees wide. For a GRB to threaten us, it would have to occur nearby, within a few thousand light years, and the jet would have to be pointed almost directly at us. Still, the possibility exists. Somewhere in the galaxy, a massive star might be nearing the end of its life, ready to collapse and produce a GRB. We wouldn't know until the gamma rays arrived, moving at the speed of light, giving no warning. While contemplating cosmic catastrophes, astronomers have also found evidence of past disasters written in the structure of galaxies themselves. Many galaxies show signs of having undergone collisions or near collisions with other galaxies. The Milky Way has tidal streams, long arcs of stars stretching across the sky that are the remnants of smaller galaxies that ventured too close and were torn apart by tidal forces. One of these streams, called the Sagittarius Stream, wraps around the entire Milky Way multiple times. It's what remains of a dwarf galaxy that collided with the Milky Way hundreds of millions of years ago. The dwarf galaxy has been passing through our galaxy repeatedly, losing more stars with each passage, gradually being consumed. Eventually, it will be completely absorbed, its stars scattered throughout the Milky Way, its identity erased. This is galactic cannibalism, the process by which large galaxies grow by consuming smaller ones. Our Milky Way is a cannibal galaxy, and the evidence of its victims is written across the night sky in streams and loops of stars that don't match the galaxy's overall structure. These are cosmic crime scenes, the remnants of gravitational violence that played out over millions of years. But galaxy collisions can create beauty as well as destruction. When two gas-rich galaxies collide, the collision compresses gas clouds, triggering intense star formation. The resulting starburst galaxies can produce new stars at rates hundreds of times higher than normal, creating brilliant clusters of young, hot stars. Some of the most spectacular images from the Hubble Space Telescope show galaxies in various stages of collision, their spiral arms distorted into fantastic shapes, glowing with newly formed stars. In about 4 billion years, the Milky Way will collide with Andromeda, our nearest large galactic neighbor. The collision will take hundreds of millions of years to complete. The two galaxies will pass through each other, then swing back together, merging in a chaotic dance of gravity. Individual stars will almost never collide, space is too empty for that, but the overall structure of both galaxies will be completely transformed. The Milky Way's elegant spiral structure will be destroyed, replaced by an elliptical blob of stars. Our solar system will survive, but the night sky will look dramatically different, filled with stars from both galaxies, eventually settling into a new configuration. The collision with Andromeda represents our galactic future, but astronomers have also uncovered evidence of our galactic past. The Milky Way wasn't always a spiral galaxy. It formed gradually over billions of years through the merger of smaller protogalaxies. By studying the chemistry and motions of stars in different parts of the galaxy, astronomers can reconstruct this history, identifying groups of stars that formed together in now destroyed dwarf galaxies. One recent discovery revealed that a major merger occurred about 10 billion years ago, when the Milky Way collided with a substantial dwarf galaxy containing billions of stars. This collision helped build the Milky Way's thick disk and halo, the regions containing older stars above and below the main spiral disk. The collision was violent enough that it might have disrupted the early disk, completely reshaping the young Milky Way. We are living in a galaxy built from the bodies of other galaxies, a cosmic Frankenstein's monster assembled from stolen parts. This history of violence is written not just in stellar positions and velocities, but in the chemistry of stars themselves. Stars formed in different environments in different galaxies have different chemical compositions. By measuring these compositions precisely, astronomers can identify which stars are native to the Milky Way and which are immigrants from consumed dwarf galaxies. It's like doing genetic testing on a cosmic scale, tracing stellar lineages back billions of years. The story of galactic evolution is more chaotic and violent than astronomers once thought. The early universe was filled with small galaxies colliding and merging, building larger structures through cosmic violence. The majestic spiral galaxies we see today are survivors, the descendants of countless collisions and mergers, and the process continues. Small galaxies are still falling into the Milky Way, still being torn apart and absorbed. We live in a galaxy that is actively cannibalizing its neighbors. But perhaps the strangest thing about galaxies is that they rotate far too quickly. This was Vera Rubin's original discovery that led to the inference of dark matter. Galaxies should fly apart given how fast they're spinning, unless something invisible is holding them together. We've known this for decades, but we still don't know what that something is. Dark matter remains the most accepted explanation, but it's an explanation that amounts to saying something we can't detect is doing this. Some physicists have proposed alternative explanations that don't require dark matter. Perhaps gravity works differently on galactic scales than we think. Perhaps Einstein's general relativity needs to be modified. Theories like modified Newtonian dynamics, or MOND, propose that gravity behaves differently at very low accelerations, becoming stronger than Newton's law predicts. MOND can explain galaxy rotation curves without dark matter, which is appealing in its simplicity. But MOND has problems. It doesn't explain gravitational lensing observations as well as dark matter does. It doesn't explain the cosmic microwave background or large-scale structure formation. It's been repeatedly modified to fix these problems, becoming increasingly complicated. Most physicists favor dark matter, despite the frustration of not being able to detect it, because it explains more observations more simply. Yet the absence of dark matter detection after decades of searching is concerning. Maybe we're looking in the wrong way. Maybe dark matter interacts with ordinary matter so weakly that our current detectors simply aren't sensitive enough. Or maybe dark matter is something completely different from what we've been assuming. Not particles at all, but some modification of spacetime itself. Some quantum effect operating on cosmic scales. The mystery deepens when we consider the distribution of dark matter in galaxies. Computer simulations of galaxy formation predict that dark matter should be densely concentrated in galaxy centers, forming cusps. But observations suggest that dark matter density is more uniform in galaxy centers, forming cores rather than cusps. This core-cusp problem has persisted for years. Either our simulations are missing some important physics, or dark matter behaves differently than we think. Some astronomers propose that dark matter might interact with itself, that dark matter particles collide with other dark matter particles, even though they don't collide with ordinary matter. This self-interaction could smooth out the cusps, creating the observed cores. It would mean dark matter has its own physics, its own forces and interactions, a hidden sector of nature we're only now beginning to explore. There might be dark atoms, dark chemistry, even dark stars made of dark matter, all invisible to us but gravitationally influencing the visible universe. This possibility is simultaneously exciting and frustrating. Exciting because it suggests a whole shadow universe coexisting with ours, a dark sector of particles and interactions paralleling ordinary matter. Frustrating because if dark matter has complex physics, detecting and understanding it becomes vastly more difficult. We would need to untangle not just one new particle, but potentially an entire periodic table of dark particles. While pondering dark matter, astronomers have also found individual objects that defy explanation. In 2015, a star designated KIC 8462852, nicknamed Tabby's star after astronomer Tabitha Boyajian, who led the study, was found to be dimming in bizarre patterns. The star would suddenly dim by large amounts, sometimes by more than 20%, then return to normal brightness. The dimming events were irregular, unpredictable, and far too large to be explained by planets passing in front of the star. Various natural explanations were proposed. Perhaps a swarm of comets was orbiting the star, occasionally blocking its light. Perhaps the star was surrounded by a disk of dust in an unusual configuration. Perhaps it was ejecting material in random directions. But none of these explanations perfectly fit the observations. Some scientists speculated that the dimming might be caused by an artificial structure, a Dyson swarm or megastructure built by an advanced civilization. If aliens were constructing an enormous array of solar panels or habitats around their star, we might observe irregular dimming as the structures blocked starlight. This explanation captured public imagination, and Tabby's star became known as the alien megastructure star. Follow-up observations eventually suggested a more mundane explanation: dust. The dimming was more pronounced at shorter wavelengths, which is what you'd expect from dust obscuration. An alien megastructure would block all wavelengths equally. The star might be surrounded by an unusual dust cloud, perhaps stirred up by collisions between asteroids or comets, or it might have a companion star that ejected dust toward the main star. But the story of Tabby's star isn't fully closed. The dust explanation doesn't perfectly account for all the observations. The star remains peculiar, one of the strangest variable stars known, and it reminds us that space contains objects whose behavior we cannot fully explain, even with our most sophisticated theories and instruments. The search for anomalies continues across all wavelengths and all classes of objects. Astronomers catalog millions of stars, galaxies, and other objects, looking for outliers, things that don't fit the patterns. Most outliers turn out to have mundane explanations once we gather enough data. But occasionally, something resists explanation, pointing toward new physics or new phenomena. This is how science progresses, by finding things that don't fit, then working to understand them. The strange objects we discover are not failures of science, but opportunities. They're nature's way of telling us our theories are incomplete, that reality is more complex than our models capture. Every unexplained observation is a potential revolution in waiting, a chance to discover something fundamentally new. And revolutions do happen. General relativity revolutionized our understanding of gravity and spacetime. Quantum mechanics revolutionized our understanding of matter and energy. The discovery of cosmic expansion revolutionized our understanding of the universe's history and fate. Each revolution emerged from taking seriously observations that didn't fit prevailing theories. What observations today might spark the next revolution? Perhaps the anomalies in galaxy rotation will lead to new physics. Perhaps the failure to detect dark matter particles will force us to reconsider what dark matter is. Perhaps fast radio bursts or strange supernovae will reveal phenomena we haven't imagined. Or perhaps the revolution will come from somewhere unexpected, from an observation that seems mundane at first, but turns out to overturn everything. The universe has been generous in providing mysteries. It has given us neutron stars and black holes, dark matter and dark energy, gamma-ray bursts and failed supernovae, interstellar visitors and strange dimming stars. Each mystery is a gift, an opportunity to learn something new about reality. Each unexplained observation is a door waiting to be opened. Behind these doors might be new physics, new particles, new forces, or they might reveal that we've been misunderstanding something fundamental about nature. Either way, the search for strange objects in space is also a search for truth, for the deepest principles governing existence. We're not just cataloging cosmic oddities, we're interrogating the universe about how it works. And the universe is answering, slowly, in whispers and hints. It's telling us that reality is stranger than we imagined, that our common sense intuitions fail at cosmic scales, that the fundamental laws of nature are subtle and surprising. It's telling us that we've barely scratched the surface, that mysteries remain to be solved, that wonder and discovery await those patient enough to observe carefully and think deeply. In dark observatories around the world, astronomers continue their vigil, watching the sky for the next surprise. Their telescopes scan the heavens, their detectors count photons, their computers analyze data. They are hunting for anomalies, for objects that don't behave as expected, for phenomena that challenge our theories. And inevitably, they will find them, because the universe is inexhaustible in its capacity to surprise us. The strangest things ever discovered in space are not endpoints, but waypoints. They mark where our understanding currently stops, where our theories break down, where reality reveals itself to be more complex than we thought. Beyond these waypoints lie territories we haven't mapped, phenomena we haven't imagined, objects we haven't dreamed of. The exploration continues, driven by curiosity and wonder, by the human desire to understand the cosmos we inhabit. And somewhere, in the vast darkness, among the billions of galaxies and trillions of stars, among the black holes and neutron stars, among the dark matter and dark energy, there are things stranger still, waiting to be found. There is a photograph that changed everything. It wasn't taken by a massive telescope atop a remote mountain. It wasn't planned by committees or funded by governments. It was taken almost as an afterthought, a request from a scientist who wanted one last look back before spacecraft left our cosmic neighborhood forever. The photograph shows Earth from beyond the orbit of Neptune, more than 4 billion miles away, appearing as a pale blue dot suspended in a sunbeam against the blackness of space. When you look at that image, when you truly comprehend what you're seeing, something shifts inside you. All of human history occurred on that tiny pixel. Every war, every love story, every scientific discovery, every work of art, all of it confined to a speck so small it's barely visible. Carl Sagan described this perspective eloquently, but words cannot fully capture the vertigo of seeing your entire world reduced to insignificance by distance and perspective. This is what studying the strange things in space ultimately teaches us. Perspective. We are small. Our planet is small. Our concerns, which seem so overwhelming, so all-consuming, are cosmically trivial. And yet, paradoxically, we are also significant. We are matter that has organized itself to contemplate matter, to understand the universe, to ask questions about existence itself. We are the universe become conscious, and that is remarkable. But perspective cuts both ways. If we are small, then the universe is vast. If we are brief, then cosmic time is eternal. If we are isolated here on Earth, then the cosmos contains mysteries we may never solve, phenomena we may never observe, truths we may never discover. The strange things we've found, neutron stars, black holes, dark matter, dark energy, failed supernovae, gamma-ray bursts, these are not the complete inventory of cosmic strangeness. They are merely what we've managed to detect so far, with our limited instruments and our limited understanding. Consider how much of the universe remains invisible to us. We can only see electromagnetic radiation, light in all its forms, from radio waves to gamma rays. But electromagnetic radiation is just one way that information can propagate through space. Gravitational waves, which we've only recently learned to detect, represent a completely different channel of information. They tell us about cosmic events in ways that light cannot, revealing phenomena that produce no electromagnetic emission. The detection of gravitational waves in 2015 opened this new window on the universe. The LIGO detectors, extraordinarily sensitive instruments capable of measuring distortions in spacetime smaller than the diameter of a proton, heard the merger of two black holes over 1 billion light-years away. The black holes, each with masses around 30 times that of the Sun, spiraled together and merged in a fraction of a second, converting 3 solar masses worth of matter entirely into gravitational wave energy. The space-time ripples from this collision spread outward at the speed of light, gradually weakening until they passed through Earth and caused LIGO's mirrors to move by less than the width of an atomic nucleus. That we could detect such a tiny effect is a testament to human ingenuity and persistence. That such events occur regularly throughout the universe is a testament to how violent and extreme cosmic processes can be. Black hole mergers release more energy in seconds than the Sun will emit in its entire lifetime, yet they produce no light at all. Without gravitational wave detectors, we would never know they happened. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of black hole mergers and several neutron star mergers. Each detection reveals something new about these extreme objects. We've found black holes more massive than we thought possible, mergers occurring more frequently than predicted, systems with properties that challenge our models of stellar evolution. And we've only just begun. Gravitational wave astronomy is in its infancy, equivalent to where optical astronomy was when Galileo first turned his telescope skyward. Future gravitational wave detectors will be even more sensitive, able to detect events from the early universe, perhaps even hearing echoes of cosmic inflation itself. There might be a gravitational wave background permeating all of space, the summed contribution of countless mergers and catastrophes throughout cosmic history, a kind of cosmic hum that carries information about the universe's earliest moments. We might detect phase transitions in the early universe, collisions between cosmic strings if they exist, or phenomena we haven't even imagined. But gravitational waves are not the only alternative channel for cosmic information. Neutrinos, nearly massless particles that barely interact with matter, stream constantly through space, passing through planets and stars as if they weren't there. The Sun produces neutrinos in enormous quantities through nuclear fusion, and we detect a tiny fraction of them with sophisticated underground detectors. But neutrinos also come from supernovae, from the cores of collapsing stars, carrying information about the physics of stellar death. In 1987, a supernova exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way visible from the southern hemisphere. The explosion, designated SN 1987A, was the closest supernova observed since the invention of the telescope. Within hours of the first light reaching Earth, neutrino detectors in Japan and the United States detected a burst of neutrinos, about 24 particles in total, captured in the brief window when the supernova's neutrino pulse passed through Earth. 24 neutrinos might not sound like much, but it was extraordinary. These particles had traveled from the core of a collapsing star, carrying information about conditions so extreme that no light could escape, conditions where matter is compressed to nuclear densities and temperatures reach billions of degrees. The neutrinos arrived hours before the first light from the supernova, because they escaped from the core immediately when the star collapsed, while light took time to work its way through the expanding debris. The detection confirmed theoretical models of core collapse supernovae. It proved that neutrinos carry away most of the energy from the collapse, far more than the visible explosion releases. It opened the era of neutrino astronomy, demonstrating that we could learn about cosmic events through neutrinos as well as light. And it raised a tantalizing question: what other neutrino sources might exist in the universe? High-energy neutrinos come from the most violent cosmic processes: supernova explosions, gamma-ray bursts, matter falling into black holes, cosmic ray collisions. The IceCube detector, built into a cubic kilometer of ice beneath the South Pole, watches for these high-energy neutrinos, looking for the telltale flashes of light they produce when they rarely interact with ice molecules. IceCube has detected neutrinos from outside our galaxy, proving that cosmic accelerators far more powerful than anything humans can build are operating throughout the universe. Some of these neutrinos have energies millions of times higher than anything we can produce in particle accelerators, energies so high that we don't fully understand how nature produces them. They must come from extraordinarily violent events, perhaps material falling into supermassive black holes, perhaps colliding neutron stars, perhaps exotic phenomena we haven't identified. Each detected neutrino is a message from cosmic violence, a clue to processes operating at the extremes of physics. And neutrinos might not be the only exotic particles streaming through space. Cosmic rays, high-energy protons and atomic nuclei, constantly bombard Earth from all directions. Most come from supernova explosions in our galaxy. But the highest energy cosmic rays, with energies millions of times higher than anything we can produce artificially, must come from sources beyond our galaxy. What accelerates particles to such energies? We don't know. The most energetic cosmic rays have energies equivalent to a baseball thrown by a professional pitcher, concentrated in a single subatomic particle. When they strike Earth's atmosphere, they create cascades of secondary particles, air showers that can contain billions of particles spread over square kilometers. Something out there is accelerating particles to these absurd energies, and we don't know what. Supermassive black holes are one possibility. Gamma-ray bursts might contribute. Perhaps there are other unknown cosmic accelerators. These alternative channels, gravitational waves, neutrinos, cosmic rays, are revealing a universe more violent and energetic than optical astronomy alone suggested. The calm, peaceful cosmos visible to our eyes is an illusion. The universe is filled with explosions, collisions, and catastrophes. Stars are constantly exploding, black holes are constantly merging, matter is constantly being accelerated to near light speed. We live in a cosmos of extremes, and we're only now developing the instruments to perceive it fully. Yet even with all these channels of information, we're still missing most of the picture. Dark matter and dark energy, which together comprise 95% of the universe's content, remain mysterious. We infer their existence from gravitational effects, but we've never directly detected particles of dark matter or measured dark energy in a laboratory. We're studying the universe while being fundamentally blind to most of what it contains. This situation is unprecedented in the history of science. Imagine trying to understand human biology while being unable to see cells, unable to detect DNA, unable to observe 95% of what makes the body function. That's the position astronomy is in today. We can see the effects, can measure the consequences, but we cannot directly observe the causes. It's like trying to understand a play by watching shadows on a wall, inferring the actors' movements from their silhouettes. Some physicists find this situation intolerable. How can we claim to understand the universe when we don't know what most of it is made of? Others argue that science has always proceeded this way. We observe effects, infer causes, make predictions, test them. The invisibility of dark matter and dark energy doesn't make them less real. It just makes them harder to study. After all, we cannot directly see atoms either, yet we've built a comprehensive understanding of atomic physics through indirect observations and experiments. The search for dark matter continues with increasing sophistication. New detectors are being built using different technologies and targeting different possible dark matter properties. Some experiments look for WIMPs, others for axions, still others for more exotic candidates. Each negative result constrains the possibilities, narrowing the parameter space where dark matter could be hiding. Eventually, we will either detect it or rule out all reasonable candidates and be forced to fundamentally reconsider our understanding of gravity and cosmology. Dark energy remains even more mysterious because we have no good theoretical handle on what it might be. The cosmological constant, a mathematical term Einstein introduced and later regretted, fits the observations perfectly. But when we try to calculate what the cosmological constant should be based on quantum field theory, we get an answer wrong by more than 100 orders of magnitude. This is the vacuum energy problem, and it represents perhaps the worst failure of theoretical physics ever recorded. Some physicists argue that the vacuum energy problem indicates we're missing something fundamental about quantum mechanics or general relativity or both. Perhaps at the deepest level, Quantum mechanics and gravity are incompatible, and we need a theory of quantum gravity to resolve the contradiction. String theory claims to provide such a theory, but it makes no testable predictions about vacuum energy. Loop quantum gravity offers an alternative approach, but it too lacks concrete predictions we can test. The absence of a quantum theory of gravity is more than an academic problem. Inside black holes, at the singularity where density becomes infinite, both quantum mechanics and general relativity are relevant, but we have no theory that combines them. We cannot predict what happens at the singularity because our physics breaks down. This is why black holes are so disturbing. They contain regions where our best theories fail, where we simply don't know what occurs. Some physicists speculate that singularities don't actually exist, that quantum effects prevent infinite density from being reached. Perhaps the center of a black hole is not a point, but a region of extremely dense but finite matter, held up by some quantum pressure we don't yet understand. Perhaps black holes are wormholes, tunnels connecting to other regions of spacetime. Perhaps there's something else entirely, something we lack the theoretical framework to even imagine. The mystery of black holes connects to another deep puzzle, the arrow of time. Why does time flow forward? Why do we remember the past but not the future? The laws of physics, with one minor exception, are time-symmetric. They work equally well whether time runs forward or backward. Yet our experience of time is profoundly asymmetric. We age, we remember, we see cause precede effect. This asymmetry seems to be related to entropy, to the second law of thermodynamics, but we don't fully understand why. Black holes complicate this picture because they have entropy. The Bekenstein-Hawking formula tells us that a black hole's entropy is proportional to the area of its event horizon. Larger black holes have more entropy than smaller ones. When matter falls into a black hole, the universe's total entropy increases because the black hole's entropy increases. But when a black hole evaporates through Hawking radiation, what happens to that entropy? Where does the information go? This is the black hole information paradox, and it's been debated for decades without resolution. Some physicists believe information is preserved somehow, perhaps encoded in the Hawking radiation in ways we don't understand. Others think information might be genuinely destroyed, violating quantum mechanics. Still, others propose that information might escape through wormholes or be stored on the event horizon in a two-dimensional pattern, a holographic encoding of the three-dimensional interior. The holographic principle suggests that all the information inside a black hole is encoded on its two-dimensional surface, like a hologram encoding three-dimensional images on a flat surface. Some physicists have extended this idea to the entire universe, proposing that our three-dimensional reality might be a holographic projection from information encoded on a distant two-dimensional boundary. It sounds like science fiction, but it emerges from serious attempts to reconcile quantum mechanics with gravity. These deep theoretical questions might seem abstract, but they have profound implications for what exists in the universe. If the holographic principle is correct, then the three-dimensional space we experience might not be fundamental. If information is preserved in black hole evaporation, there might be subtle correlations in Hawking radiation that we could potentially detect. If quantum gravity prevents singularities, then the centers of black holes might contain exotic states of matter that could leave observable signatures. The strangest things in space might not be objects at all, but properties of spacetime itself. Quantum mechanics tells us that empty space is not truly empty. It seethes with virtual particles that briefly pop into existence and annihilate. These quantum fluctuations have measurable effects, creating forces between uncharged plates and shifting atomic energy levels. At extreme energies, near black holes or in the early universe, quantum fluctuations might become macroscopic, creating bubbles of different vacuum states or generating gravitational waves. Some versions of cosmic inflation propose that our entire observable universe is just one bubble in an eternally inflating multiverse, with new bubble universes constantly forming. Each bubble might have different physical constants, different numbers of dimensions, different particles and forces. If this is correct, then the universe we observe is just one tiny region of a vastly larger reality, and most of that reality is forever beyond our reach, separated from us by eternally inflating space. The multiverse hypothesis is controversial because it's potentially untestable. If other universes are causally disconnected from ours, we cannot observe them or interact with them. Science traditionally requires testability. Theories must make predictions we can check. But if the multiverse exists, we might never be able to test its existence directly. We could only infer it from theoretical consistency and from explaining the apparent fine-tuning of physical constants. This raises philosophical questions about what counts as science. Is a theory that explains observations but cannot be directly tested still scientific? Many physicists say yes, arguing that inference to the best explanation is scientifically legitimate even without direct observation. Others disagree, maintaining that untestable theories are metaphysics, not physics. The debate continues with no clear resolution. But regardless of whether the multiverse exists, we live in this universe, and it contains wonders and mysteries enough to occupy us for centuries. Every answer we find generates new questions. We explained cosmic acceleration with dark energy, but now we must explain dark energy. We explained galaxy rotation with dark matter, but now we must explain dark matter. We explained pulsars with neutron stars, but now magnetars and strange stars pose new puzzles. Strange stars, or quark stars, are hypothetical objects where matter is compressed beyond neutron star densities, causing neutrons to break down into their constituent quarks. In a quark star, there are no individual protons or neutrons, just a sea of free quarks held together by the strong nuclear force. Such objects might exist at the boundary between neutron stars and black holes, at masses just barely below the threshold for gravitational collapse. We don't know if quark stars exist because we can't easily distinguish them from neutron stars observationally. They would be slightly smaller and denser than neutron stars of the same mass, but the difference might be subtle. Some anomalous neutron stars might actually be quark stars, but we have no definitive proof. It's possible that some stellar cores collapse directly into black holes, skipping the quark star phase entirely. Or perhaps quark stars are common, but indistinguishable from neutron stars with current observations. Even more exotic possibilities exist. Hypothetical preon stars, made of particles even more fundamental than quarks, might exist at even higher densities, electroweak stars held up by radiation. Pressure from electroweak interactions might briefly exist during core collapse. Gravastars, theoretical alternatives to black holes where spacetime forms a stable shell rather than a singularity, might account for some black hole observations. We simply don't know what exists at the absolute extremes of density and gravity. The more we learn, the more possibilities open up. This is both exciting and humbling. Exciting because it means endless opportunities for discovery, endless new phenomena to observe and understand. Humbling because it reveals how little we currently know, how vast the territory of ignorance remains. We've mapped some coastlines of the continent of knowledge, but the interior remains mostly unexplored. And there are hints, tantalizing suggestions that we might be missing entire categories of phenomena. Some astronomers have proposed that primordial black holes, formed in the early universe rather than from stellar collapse, might account for some dark matter. These black holes would have been created from density fluctuations in the first fraction of a second after the Big Bang, ranging in mass from microscopic to thousands of solar masses. If they exist in sufficient numbers, their gravitational effects could explain galaxy rotation curves and gravitational lensing observations without requiring exotic particles. Primordial black holes would be difficult to detect because they emit no light and are likely spread diffusely through space. But they might occasionally pass through our solar system, causing subtle gravitational effects on planetary orbits or spacecraft trajectories. They might lend starlight, creating brief brightening events we could detect with careful monitoring. They might evaporate through Hawking radiation, creating brief gamma-ray flashes. Several teams are searching for these signatures, so far without success, but the parameter space is large. Another speculative possibility involves cosmic strings, defects in spacetime that might have formed during phase transitions in the early universe. Cosmic strings would be extraordinarily thin but immensely massive, and they might stretch across cosmic distances. If they exist, they would gravitationally lens light in distinctive ways, creating double images of background galaxies. They might generate gravitational waves as they oscillate and interact. They might serve as seeds for structure formation, helping galaxies form in the early universe. Despite extensive searches, no cosmic strings have been definitively detected. But absence of evidence is not evidence of absence. Cosmic strings might be rare, with only a few existing in the observable universe, or they might be common but difficult to detect with current instruments. Or they might not exist at all, a prediction of theories that turn out to be wrong. We won't know until we either find them or rule them out completely. These exotic possibilities remind us that the universe might be stranger than we can imagine, not just stranger than we have imagined. Our theories are based on extrapolating from what we know, but reality is under no obligation to conform to our extrapolations. Nature might have surprises in store that our current physics cannot even conceptualize. Consider, before we discovered radioactivity, we had no concept that atoms could spontaneously decay. Before quantum mechanics, we had no idea that particles could tunnel through barriers or exist in superpositions. Before general relativity, we didn't know that gravity could be understood as space-time curvature. Each of these discoveries revealed aspects of reality that were literally inconceivable within previous theoretical frameworks. What current conceptual blindness might we suffer from? What phenomena might exist that we lack the theoretical vocabulary to describe? Perhaps there are particles that don't fit into our standard model, forces that operate only at cosmic scales, dimensions we cannot perceive, aspects of consciousness or mathematics or information that play physical roles we haven't recognized. We should remain humble about the completeness of our knowledge. Yet despite this humility, despite recognizing how much we don't know, we should also celebrate how much we do know. We've mapped the observable universe, traced cosmic history back to microseconds after the Big Bang, understood the life cycles of stars, discovered thousands of planets around other stars, detected gravitational waves from colliding black holes, built theoretical frameworks that explain phenomena from subatomic particles to cosmic structure. This is an extraordinary achievement for a species that evolved to hunt and gather on an African savanna, whose brains were shaped by natural selection for survival and reproduction, not for understanding quantum mechanics or cosmology. The fact that we can comprehend the universe at all is remarkable. The fact that we've made the progress we have in just a few centuries is astonishing. And the journey continues. New telescopes are being built, space telescopes that will peer deeper into the universe than ever before, ground-based telescopes with mirrors tens of meters across, radio telescope arrays spanning continents. New detectors are coming online, gravitational wave observatories with enhanced sensitivity, neutrino detectors monitoring cubic kilometers of ocean or ice, particle detectors searching for dark matter with unprecedented precision. Each new instrument expands our observational reach, revealing phenomena we couldn't previously detect. Each new observation constrains our theories, ruling out some possibilities and confirming others. Each discovery answers old questions and raises new ones, pushing the boundary of knowledge outward while simultaneously revealing how much further that boundary extends. The strangest things ever discovered in space, neutron stars, black holes, dark matter, dark energy, gamma-ray bursts, failed supernovae, interstellar visitors, mysterious dimming stars, are not the end of the story. They are chapters in an ongoing narrative, a story of human curiosity and ingenuity confronting the vast mysteries of existence. Each strange object is a clue, a piece of a puzzle we're slowly assembling, a window into aspects of reality we're only beginning to understand. And beyond these windows lies the vast cosmos, ancient and mysterious, filled with phenomena we haven't detected, objects we haven't imagined, principles we haven't discovered. The universe is under no obligation to make sense to us, to conform to our expectations, to reveal its secrets on our timescale. but it has been generous so far, offering wonders and mysteries in abundance, challenging us to reach beyond our limitations and comprehend the incomprehensible. We stand on Earth, looking up at the stars, and we see ghosts and echoes from the past. We see neutron stars spinning hundreds of times per second, black holes with masses billions of times that of the Sun, galaxies colliding across millions of years, dark matter holding everything together while dark energy pushes everything apart. We see a universe stranger than we imagined, and we understand, or are beginning to understand, how it works. This is the human achievement, to take the raw data of photons and gravitational waves and neutrinos, to apply mathematics and physics and creativity, and to build from these ingredients a comprehensive picture of cosmic reality. We are small, yes, but our understanding is not. We are brief, yes, but our knowledge transcends our individual lifespans, accumulated and refined across generations. We are isolated on one planet, yes, but our instruments reach across billions of light years. Our theories encompass the entire observable universe. The strangest things in space are not just objects to be catalogued or phenomena to be explained. They are invitations to wonder, calls to curiosity, demonstrations that reality is richer and more complex than common sense suggests. They remind us that the universe is not built for our convenience or comprehension, that it operates according to its own principles, that it owes us no explanations. Yet we persist in asking questions, in building instruments, in developing theories, in trying to understand. This persistence, this curiosity, this drive to know, this might be the strangest thing of all. That matter can organize itself to contemplate matter, that the universe can become conscious and study itself, that a species confined to one small planet can discover black holes and dark energy and gravitational waves. This is the deepest mystery, and perhaps the most wondrous. The night sky still holds secrets, objects we cannot yet detect, phenomena we cannot yet explain, principles we cannot yet articulate. The journey of discovery continues, driven by curiosity and wonder, by the desire to know what lies beyond the next horizon. And the universe waits, patient and eternal, ready to reveal its next surprise to those who have the courage and persistence to look. There are moments in science when everything you thought you understood suddenly becomes uncertain. When an observation is so unexpected, so contrary to established theory, that it forces you to question whether your instruments are broken or your understanding is incomplete. These moments are rare and precious. They are when revolutions begin. In October 2017, astronomers detected something that shouldn't exist according to our understanding of the solar system's formation. A telescope in Hawaii, part of a survey designed to detect near-Earth asteroids, captured an object moving through the inner solar system at high speed. At first, it seemed unremarkable. Telescopes detect asteroids constantly. But as astronomers calculated its trajectory, they realized something extraordinary. The object had come from interstellar space. This was Oumuamua, which we discussed earlier, but its strangeness goes deeper than we initially acknowledged. As more data accumulated, as more telescopes tracked its path, the anomalies multiplied. The object was tumbling in a complex pattern, rotating around multiple axes simultaneously. This kind of rotation is unusual. Most asteroids settle into simple spins around a single axis. But Oumuamua was wobbling chaotically, as if something had disturbed it, or as if its mass was distributed in some highly irregular way. Then there was its shape. Based on how its brightness varied as it rotated, astronomers calculated that Oumuamua was extremely elongated, perhaps 10 times longer than it was wide, maybe more. Some estimates suggested it might be even more extreme, a needle-shaped object unlike anything we've seen before. No natural process we know of creates such elongated objects. Asteroids are typically round or potato-shaped, ground down by billions of years of collisions. Comets can be irregular, but not to this extreme. And most troubling was its acceleration. As Oumuamua moved away from the sun, something pushed it, giving it a tiny but measurable boost in velocity. Comets do this. The sun's heat vaporizes ice, creating jets of gas that act like tiny rocket engines. But Oumuamua showed no signs of outgassing, no tail, no coma, no spectroscopic evidence of volatiles evaporating. Yet it accelerated anyway. Every proposed explanation had problems. Maybe it was a comet made of unusual material that doesn't produce visible outgassing. But what material? Maybe it was a fractal aggregate of dust, so porous that it could accelerate through subtle effects. But why would it be so elongated? Maybe the acceleration was caused by radiation pressure on a thin, flat object. But natural processes don't create thin, flat objects. One astronomer, Avi Loeb of Harvard, proposed that we should seriously consider the possibility that Oumuamua was artificial. A light sail, perhaps a defunct probe from an alien civilization, drifting through the galaxy like a derelict ship. The scientific community largely rejected this hypothesis, and for good reason. Extraordinary claims require extraordinary evidence, and we have no extraordinary evidence. But we also have no satisfactory natural explanation. Oumuamua remains an enigma, now too distant to study further, receding into the darkness carrying its secrets with it. The debate over Oumuamua reveals something important about how science operates at the boundaries of knowledge. We have a strong preference for natural explanations, for hypotheses that fit within our existing frameworks. This is reasonable. Most anomalies turn out to have mundane explanations once we gather enough data. But this preference can also become a bias, causing us to contort ourselves into increasingly unlikely natural explanations rather than consider genuinely novel possibilities. What if Oumuamua was artificial? What if we're living in a galaxy where technological civilizations occasionally send probes into interstellar space and we happen to detect one passing through? The probability seems low, but we have no good way to calculate it. We don't know how common technological civilizations are, how often they send probes, how long the probes last. Maybe the galaxy is filled with ancient artifacts, derelict technology from civilizations that rose and fell millions of years ago. Maybe Oumuamua is just the first one we happen to notice. This possibility leads to a disturbing thought. What if we've already seen evidence of alien technology and dismissed it as natural? What if some of the strange objects we've cataloged, some of the unexplained phenomena we've detected, are actually artificial, but we lack the conceptual framework to recognize them as such? We assume that alien technology would be obviously artificial, but perhaps advanced technology is indistinguishable from natural phenomena, operating according to physical principles we don't yet understand. Consider fast radio bursts again. Those mysterious millisecond pulses of radio waves from distant galaxies. We've found natural explanations that seem to work. Magnetars, colliding neutron stars, other extreme astrophysical events. But what if some FRBs are artificial? What if they're communication signals or energy beams used to propel spacecraft or byproducts of technologies we cannot imagine? We would have no way to tell unless we detected patterns in the signals, repetition, or structure that couldn't be natural. Some astronomers have suggested searching for such patterns, looking for prime numbers or mathematical sequences in FRB timing or frequency structure. So far, nothing conclusive has been found, but the searches continue. If we did find structure, if we did detect patterns that couldn't be natural, it would be the most important discovery in human history. It would prove we're not alone, that intelligence and technology have emerged elsewhere in the cosmos, that life is not confined to Earth. But the silence is deafening. Decades of SETI searches have found nothing definitive. The galaxy seems empty of radio signals from technological civilizations. This is the Fermi paradox. If intelligent life is common, if it develops technology, if it explores or communicates, where is everyone? Where are the signals, the probes, the artifacts, the evidence? Perhaps intelligence is rare, emerging only once in a galaxy or once in many galaxies. Perhaps technological civilizations tend to destroy themselves quickly through nuclear war or environmental collapse or other catastrophes before they can colonize space or send signals far. Perhaps they exist, but choose silence, hiding from potential threats, or following some prime directive of non-interference. Perhaps they communicate using methods we haven't thought to monitor. Or perhaps the galaxy is filled with intelligence, but it's so different from us that we don't recognize it. Perhaps advanced civilizations transcend biology, uploading themselves into computational substrates, becoming entities we would struggle to identify as alive or conscious. Perhaps they retreat into virtual realities, finding simulated worlds more interesting than physical exploration. Perhaps they engineer themselves or their environment so thoroughly that they become indistinguishable from natural phenomena. This last possibility is particularly unsettling. What would a truly advanced civilization look like? Not advanced by decades or centuries, but by millions of years. Their technology would be based on physical principles we haven't discovered. Their structures would operate on scales we can't perceive. Their motivations and thought processes might be incomprehensible to us. Trying to understand such a civilization might be like an ant trying to understand human civilization. The gap in complexity and capability would be too vast. There's a concept called the Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev, that classifies civilizations by their energy consumption. A Type 1 civilization can harness all the energy available on its planet. A Type 2 civilization can harness all the energy of its star, perhaps by building a Dyson sphere. A Type 3 civilization can harness all the energy of its galaxy. Humanity is currently around Type 0.7, not even fully Type 1 yet. But the Kardashev scale might be misleading. It assumes that advanced civilizations want to maximize energy consumption, that they expand and build megastructures, that they leave obvious signatures we can detect. Perhaps this is wrong. Perhaps truly advanced civilizations become more efficient, not more consumptive. Perhaps they miniaturize, operating at quantum scales, achieving more with less. Perhaps they transcend physical needs entirely. If so, we might be surrounded by advanced civilizations and never know it. They might be operating on scales or in ways we cannot detect with our instruments. They might be using communication channels we haven't discovered, gravitational wave modulation, neutrino beams, quantum entanglement somehow, or something entirely beyond our physics. We might be like radio receivers trying to detect a civilization that communicates only with fiber optics. We're looking in the right general area but at the wrong phenomenon. This brings us back to the fundamental question: how much of the universe are we missing? We've discussed dark matter and dark energy, which together comprise most of the universe's content. But perhaps there are other components we haven't detected, phenomena that interact with ordinary matter so weakly that we've never noticed them. Perhaps there are particles that exist, but leave no trace in our detectors, fields that permeate space but produce no measurable effects with current technology, dimensions that are curled up too small for us to probe. String theory proposes that the universe has extra spatial dimensions beyond the 3 we experience, perhaps 6 or 7 additional dimensions curled up at scales far too small to observe directly. If these dimensions exist, there could be entire realms of physics operating within them, particles and forces and structures that we cannot access because we're confined to 3 spatial dimensions. It would be like living on a 2-dimensional sheet of paper, unaware that a 3-dimensional world exists all around us. Some versions of string theory propose that our entire universe is a 3-dimensional brain, a membrane floating in a higher dimensional space. There might be other brains, other universes, existing parallel to ours, separated by microscopic distances in extra dimensions, but forever inaccessible because we cannot move through those dimensions. Occasionally, these brains might interact, producing effects we would observe as mysterious forces or particles or symmetry breakings. This is highly speculative, untested, perhaps untestable. But it represents serious attempts by physicists to extend our understanding beyond what we can directly observe. And it raises the possibility that the strangest things in space might not be the things we can see, but the things we cannot, the phenomena occurring in extra dimensions, the interactions between brains, the physics of the bulk space in which our brain floats. Even within the 4 dimensions we can access, there might be aspects of reality we're missing. Quantum mechanics tells us that particles can exist in superpositions, occupying multiple states simultaneously until measured. But what counts as a measurement? What causes a quantum system to collapse from superposition to a definite state? This is the measurement problem, one of the deepest puzzles in quantum mechanics, debated for almost a century without consensus. Some interpretations of quantum mechanics propose that superpositions never actually collapse, that every quantum measurement causes the universe to split into multiple branches, each experiencing a different outcome. This is the many worlds interpretation, and it suggests that reality is vastly larger than we observe. Every quantum event spawns countless parallel universes, all equally real, all existing simultaneously in a vast quantum multiverse. If many worlds is correct, then for every strange object we observe in space, there are universes where it evolved differently, where history took another path. There are universes where Earth never formed, where life never emerged, where dinosaurs still rule. There are universes where humans develop differently, where history unfolded in radically different ways. Every possible quantum outcome is realized somewhere in the multiverse. This sounds like science fiction, but it's a serious interpretation of quantum mechanics, taken seriously by many physicists. The alternative interpretations, Copenhagen, objective collapse, pilot wave theory, all have their own strangeness, their own implications. Quantum mechanics forces us to confront the weirdness of reality at a fundamental level, and none of the interpretations feel satisfactory. Reality at the quantum level is genuinely strange, operating according to rules that violate our common sense, and quantum effects might not be confined to the microscopic realm. Some experiments suggest that quantum coherence, the maintenance of superposition states, can persist in surprisingly large and warm systems far beyond what classical physics would predict. There are hints that quantum effects might play roles in biology, in photosynthesis and bird navigation, and possibly even in consciousness. If so, then the strangeness of quantum mechanics isn't just a feature of subatomic particles, but something that permeates all of reality, including our own minds. This leads to one of the most profound mysteries in all of science: consciousness itself. How does subjective experience arise from physical processes? How do the electrochemical signals in a brain give rise to the feeling of being, to the sensation of existing as a conscious entity? We have no good answer. We can map neural correlates of consciousness, can identify which brain regions are active during different conscious states, but we cannot explain why or how physical processes generate subjective experience. Some philosophers argue that consciousness might be fundamental, not reducible to simpler components, just as fundamental as space and time and matter. Some physicists speculate that consciousness might be related to quantum effects, to the collapse of wave functions, to observation itself. Perhaps consciousness is what resolves quantum superpositions, what makes reality definite. Perhaps the universe needs observers to be real, and consciousness is the universe's way of observing itself. These ideas venture far beyond confirmed science into speculation, but they're motivated by genuine mysteries. We don't understand consciousness. We don't understand quantum mechanics. Perhaps these two mysteries are related. Perhaps understanding one will illuminate the other, or perhaps they're separate phenomena that just happen to both be profoundly weird. The point is that the strange things in space, the neutron stars and black holes and dark matter and dark energy, are symptoms of a deeper strangeness, hints that reality at its foundations operates in ways we don't fully grasp. Every layer of understanding we peel back reveals new mysteries underneath. We explain atoms with quantum mechanics, but quantum mechanics itself is deeply mysterious. We explain cosmic expansion with dark energy, but dark energy is even more mysterious than the expansion it explains. Perhaps this is how science always works, trading one mystery for another, hopefully getting deeper and more fundamental with each trade. Or perhaps we're approaching limits, boundaries beyond which human understanding cannot pass. Our brains are finite structures, shaped by evolution for survival on Earth, not for comprehending the cosmos. Maybe there are truths about reality that we can never access, not because they're hidden, but because we lack the cognitive architecture to represent them. This is a humbling thought, but not a defeating one. Even if we cannot understand everything, we can understand more than we do now. Even if there are limits to human knowledge, we haven't reached them yet. The history of science is a history of overcoming apparent limits, of discovering that what seemed impossible was merely difficult, that what seemed beyond comprehension was just beyond current comprehension. And strange objects in space continue to surprise us. In recent years, astronomers have detected objects that might be intermediate mass black holes, filling the gap between stellar mass black holes of tens of solar masses and supermassive black holes of millions of solar masses. These intermediate mass black holes, with masses of hundreds or thousands of solar masses, have been theoretically predicted but rarely observed. Their existence would help explain how supermassive black holes form. Perhaps they grow from intermediate mass seeds rather than from stellar mass black holes. But intermediate mass black holes are difficult to detect because they are not actively accreting matter and thus produce no bright emissions. We find them through subtle gravitational effects, through their influence on nearby stars, or through gravitational wave detections when they merge with other black holes. Each discovery helps fill in the picture of how black holes grow and evolve. But each discovery also raises new questions about formation mechanisms and growth rates. Similarly, astronomers have found ultra-compact dwarf galaxies, objects that seem to be hybrids between globular clusters and galaxies. They contain millions of stars packed into regions only a few hundred light-years across, with densities far higher than normal galaxies but lower than globular clusters. Are they very large? Globular clusters or very small galaxies? The distinction might seem semantic, but it has implications for how structures form in the universe. Some ultracompact dwarfs might be the stripped cores of larger galaxies that passed too close to massive neighbors and lost their outer stars to tidal forces. Others might have formed independently in high-pressure environments in the early universe. Studying them helps us understand the range of ways that stellar systems can form and evolve, pushing the boundaries of what we thought possible. And then there are objects that seem to violate conservation laws, at least temporarily. Blazars are galaxies with jets of material streaming from their central black holes pointed almost directly at Earth. These jets move at nearly the speed of light, and due to relativistic effects, they can appear to be moving faster than light. An illusion caused by the geometry of the situation, but an illusion that took decades to fully understand. Blazars can vary in brightness dramatically over very short timescales, changing by factors of 10 in days or hours, implying that enormous amounts of energy are being generated in tiny regions near the black hole. The physics of blazars pushes our models to their limits. We're trying to understand what happens when jets moving at 99% of the speed of light interact with magnetic fields and matter, when relativistic particles collide with photons and boost them to gamma-ray energies, when black holes swallow matter and convert it to energy with efficiencies far exceeding nuclear fusion. We have theoretical models, but the details remain uncertain, the observations often surprising. Each class of object we study reveals new complexities, new edge cases, new phenomena that challenge our understanding. This is as it should be. If nature were simple, if all objects fit neatly into our categories, if nothing surprised us, science would be finished. But nature is not simple. Every object is unique in some way. Every system has its quirks. Every observation contains information we weren't expecting. The strangest things in space teach us humility. They remind us that the universe doesn't care about our theories, that it will do whatever physics allows regardless of what we find intuitive or elegant. They push us to expand our models, to consider possibilities we hadn't imagined, to remain open to being wrong about things we thought we understood. And they inspire wonder. Even after decades of studying astronomy, even after seeing thousands of images and reading countless papers, astronomers still experience moments of awe when confronted with new observations. The universe keeps delivering surprises, keeps showing us things we didn't predict, keeps demonstrating that reality is richer than our imaginations. This sense of wonder is what drives science forward. It's not just about solving puzzles or publishing papers or winning prizes. It's about standing under the night, the ET sky, and knowing that those points of light are entire suns, that around those suns might be planets, that on those planets might be life, that in that vast darkness are objects stranger than we've imagined. Black holes and magnetars and dark matter and dark energy and perhaps things we haven't even conceived of yet. And it's about knowing that we can understand, at least partially, at least imperfectly, what's out there. That with telescopes and mathematics and persistence, we can decode the messages carried by light from distant stars, can reconstruct events that occurred billions of years ago, can predict what will happen billions of years hence. We are finite beings comprehending an infinite cosmos, and that is miraculous. The search continues. Telescopes scan the skies, detectors count particles, computers crunch data, scientists debate theories. New observations are made daily, new papers published weekly, new questions posed constantly. The inventory of strange objects grows longer, the list of mysteries deeper. We are simultaneously learning more and realizing how much we don't know, making progress and discovering how far we have to go. And somewhere out there, in the depths of space, in regions we haven't observed, at scales we haven't probed, there are things stranger still. Objects that will force us to revise our theories, phenomena that will challenge our assumptions, discoveries that will reshape our understanding of reality. The universe is vast and ancient and full of secrets, and we've barely begun to explore it. The strangest things ever discovered in space are not the end of strangeness, but the beginning. They are the first hints of a cosmos far more complex and mysterious than we imagined, far more rich with phenomena and possibilities than our theories encompass. They are invitations to keep looking, keep questioning, keep exploring, and we accept those invitations driven by curiosity and wonder, by the fundamental human desire to understand the world we inhabit and our place within it. The night sky remains, as it has always been, an endless source of mystery and revelation, and we remain, as we've always been, cosmic explorers seeking to understand our strange and beautiful universe.